get a single 10 on your
Okay.
quizzes. I'm looking forward to it.
Oh, that's a goal to aim for. Anyway, we're going to continue.
Can I go for the quiz?
Last time, we spoke about two forms for a matrix, the reducer echelon form and the row echelon form. We also actually put a matrix in reducer echelon form. So we actually did the process of that. So now, I kind of touched on this before, but now I want to show you some other possibilities about the possibilities for solutions to a linear system, and that we can figure it out based on the reducer echelon form. So we're moving on to chapter 3. It's entitled Varieties of Solutions for Linear Systems. It turns out that if you're solving a linear system of equations, there are only 3 possibilities for the solutions that you can have. And I'm going to describe them to you now. So we'll illustrate with some examples, just to again get used to putting things in the reducer echelon form, because it is something you would be expected to be able to do on a test. And so the more practice you get, the better. So let's actually just solve the system. And of course, we're going to use linear algebra. So here's the first example. So we want to use linear algebra, and so what would be the first step here?
Excuse me.
Can you see?
Augment the matrix.
Augment the matrix. And so minus 2, 1, minus 1, 4, 1, 2, 3, 13, 3, 0, 1, minus 1. Throw it out all in a matrix, and now we're going to find the reducer or echelon form. So basically, if you're asked to solve a system in this class, this is kind of the process. This is one of the processes that you can go through. Step 1 is to augment the system. Step 2, find the row echelon form or reduce row echelon form. At this point, it's kind of a preference. If the goal is to solve the system, it's your preference. You'll get to this one quicker than that one, but you might prefer to just go further. So let's actually do that. So what is the first thing you do here?
Switch the second row with the first row.
Put row 2 here. And then I immediately want to get zeros here. So what I can do is I'm going to use the minus 2 to eliminate this. So I can take row 2 plus 2 row 1. So multiply this by 2, add it to that, I get 0. 2 times this is 4, plus this is 5. 2 times this is 6, plus that is 5. 2 times this is 26, plus that, 30. And then I'm going to want to eliminate this guy, so probably what I would do is I would take row 3 minus 3 row 2. So this minus 3 is 0. This minus 3 times that is minus 6. This minus 9 8. Minus 1 minus 39 minus 40.
For the second one, isn't it R2 plus R1?
For the second one,
Yeah, isn't it?
2 times this plus that.
So it's
So, yeah, this is row 1 plus 2 row 2. And we keep going, right? So the very next thing, we've established the first pivot. Notice that there are only zeros below him. The next step is to establish the second pivot. So I'm going to want to turn that into a 1. The quickest way is, of course, to divide by 5. 6. So this is row 2 divided by 5. Can I simplify this any? Like 2 goes into everyone, right? Let's divide by minus 2. Get this 3, 4, 20. Now we're on to the next step. Since I want to establish this pivot, I want to get a 0 here. So how can I get a 0 there?
row 3 minus 3 times row 2? Yeah.
Row 3 minus,
Professor,
3 times row 2.
what is this? Is it a 0 after the 1 on the third row, second?
here.
So third row and the 2. So 3, 2. Yeah. What is this number 3 or?
That's a 3.
That's
Yeah.
a 3. Okay.
Okay, so now we're going to take row 3 minus 3 times that, was what was suggested. So take this time minus 3 times that, 0. This minus 3 times that, 0. This minus 3 times that, 1. This minus 3 times that, 2. Right. Now this part, you can realize that you're in row echelon form. Last time we brought this matrix to reducer echelon form, so you can look at that part. But I want to stop here in this example. I don't know if you realize it, but this is the guy that we did last time, and we went all the way down to row echelon form. But if we're solving a system, we don't have to go that far. We can actually stop here. So here's the idea. Now remember, the columns of our matrix correspond to different variables, right? So the first column is the x1, second column is x2, third column is x3. Same thing holds here. x1, x2, x3. And we also remember that the rows of the augmented matrix represent equations, right? So if you look at, and so now this is step 3. Read all solutions from the bottom row up. So if you look in the last row, this corresponds to an equation, right? What does that equation say?
X3 equals 2.
That says x3 is equal to 2. So I know the value of x3. And so now we move up to row 2. What does row 2 say? x2 plus x3 equals 6. But I know that this guy is 2. This means that x2 is equal to 4. Then you move up to the next row, row 1. Alright, so we go from the bottom up because we're back substituting all the way up. And by the time we get to the top, we should be able to have found everyone. So the first one says x1 plus 2x2 plus 3x3 equals 13. But I know what these two are. So this means that my x1 plus 2 times x2 plus 3 times x3 equals 13. And so this means that my x1 would be equal to what? So my x3 is 2, x2 is 4, x1 is negative 1. Here's how we write the solution. It's customary for us to write them as column vectors, so that's what we're going to do. x1, x2, x3 is equal to, now we just put it in the values. x1 was minus 1, x2 was 4, and x3 was 2. So this is the solution to the system. This gives us case 1 for a variety of solution. This guy is called the unique solution. Meaning there is a solution to the system and there is only one vector that solves the system, namely this vector solves the system. I have to plug in this value for x1, x2, x3, and that will be the only solution to the system. When you have such a case, you say that your system has a unique solution. There's only one vector that solves the system.
Professor,
Yes.
what about like instead of read of solution from bottom row up, what if you do it from the top row to the bottom?
Well, if we start at the top row, we'd start with this. Can you tell me anyone from that?
No.
No. There are 3 unknowns and 1 equation.
Okay.
That's why you start from the bottom row up. You're killing, the point of putting in row echelon form is you're killing all the other variables, and you'd have killed the most in the bottom row, just by the form of how you set it up.
So this time you stopped at the reduced
row
echelon form, but if you stop at the reduced row echelon form, would you get the same solution?
Yeah, in fact, the reduced row echelon form for this would have been 1, 0, 0, minus 1, 0, 1, 0, 4, 0, 0, 1, 2.
How do you know?
Well, for 1, we did that last time, and for
okay.
secondly, I actually know what the solution is.
Oh, okay.
So my x3 must be 2, my 0x1 plus 0x2 plus 0x3 must be 4, and my 1x1 plus 0x2 plus 0x3 must be minus 1. So if you had went further, to the reduced echelon form, it would save you a little work here. You'll ultimately get to the same answer. The reason why I might require you on a test or a quiz to go all the way to here is that because in row echelon form there is no unique
Solution.
There's no unique way to write a row echelon form. So it's possible for all of you to have different numbers in this matrix, and that's harder to grade. So, but once you get to this, there's literally only one way to write down the reduced row echelon form. Everyone's answer has to look the same, or else so I can know who made a mistake. Because a different set of row operations can give you a different looking matrix at this level. But once you get to the reduced echelon form level, they would all converge to the same matrix. So that's one case, the unique solution case, case 1. You can have one vector that solves your system. Here's another example. Solve this system. x1 minus 2x2 plus 3x3 equals minus 2. Minus x1 plus x2 minus 2x3 equals 3. 2x1 minus x2 plus 3x3 equals 1. Again, we do the same thing. throw this guy into an augmented matrix. 1, minus 2, 3, minus 2, minus 1, 1, minus 2, 3, 2, minus 1, 3, 1. And now I want to find the row echelon form of this guy. So I already have a 1 here, so I'm going to leave that guy. If I want to get 0 here, so what I can do is I can just add row 1 and row 2. Adding those two would give me a 0. Add these two, I get a minus 1. Add these two, I get a 1. Add these two, I get a 1. And to kill this 0, I can just take
R3 plus 2R1.
what?
R3 plus 2R1.
R3 plus 2R1.
Negative 2.
2R1.
Or 2R2 you mean?
2R.
Again, there are multiple ways to do this. This is the whole problem. So if I multiply this row by 2, and I'm going to add it to that. So minus 2, 0, 2, and add it to that, 1. Minus 4, add it to that, minus 1. 2 times this, 6, add it to that, 7. So now I want to turn this into a pivot and kill that one. So I'm going to 1, minus 2, 3, minus 2. 0, 1, minus 1, 1. That's just row 2 times minus 1. And to make this a 0, I can just add these two rows. So 0 plus 0, 0. Minus 1 plus 1, 0. This plus that, 0. This plus that, 8. That's the REF form, which means it's good enough to actually start solving the system. Now let's start doing what we did before. Start from the bottom row up. What does row 3 tell us?
3 equal to nothing. Everything is 0.
Exactly.
So you don't get everything. I look
Yes,
at
exactly.
X3 from last time, I was like, you will get something.
Exactly. Look at what row 3 says. Row 3 says
0 plus
0 plus 0 plus 0 equals 8.
Yeah, that's a new theory.
That is obviously makes no sense. That is a contradiction, right? When that happens, basically what that means is obviously 0 is not equal to 8, but for this system to have a solution, 0 has to be equal to 8. This means the system has no solution. It's possible for a system to not have a solution. So this is case 2. For the variety of solutions. No solutions. So if you have a linear system, one possibility is you can solve that system and you will get one vector that solves that system. You have a unique solution. Another possibility is you get something completely crazy which can't possibly be true, and hence you get no solution. Let me say a little bit more about this. There are two types of systems that we will look at, the ones that we can find some solution for and the ones that have no solution. Systems that do not have solution are called inconsistent. It is inconsistent with the rules of mathematics for 0 to be equal to 8.
Professor,
Yes?
so here when you get something like that, 0 plus 0, 0, whatever, 8, don't you go to the like second row and first row, or you just stop there?
No, because what does it mean to solve a system? It means you need to find values for the variables that work in all the equations. If it's impossible to find a value that works in one of the equations, it's possible to find a value that works in the entire system. Because the work for the system means you work for all equations in the system. Clearly, this equation has no solution. It's impossible to find x values that will make that true. So if I don't care about the others, there's no point in looking. Right? Once one equation messes up, the whole thing messes up. Right? Solving a system means finding values for the variables that will work in all equations. And that one will never work no matter what. So we say that this is an example of what we call an inconsistent system. We say this is inconsistent. The first example I did was an example of a consistent system. It had one solution. How you can identify this? Sometimes they're row echelon form, but especially from their reduced. We can recognize when a system is inconsistent by its reduced row echelon form. There will be a row that looks like this. Bunch of zeros, and then in the last position you're going to have some number that's not 0. Right? Every inconsistent system will have that in common. Right? How you can know a system has no solution is when you find its reduced or echelon form, something like this is going to happen when you start eliminating things and trying to put it in the right form. And that's what happened here in the last line.
If a is equal to 0, then we're going to have multiple solutions, right? And
we'll see. Well, we're going to do, I'm not done with all the cases. We've only looked at 2 so far. There are more. So we'll look at the case where a equals 0. Right? But as far as you're concerned, at this point, once you start doing a reduced or echelon form, and you end up with something with all zeros on this side, except over here in the constant column, there is a non-zero number. That can't possibly make sense. That says 0 is not equal to 0. You say that's an inconsistent system, there's no solution, and you stop there. Let's look at another example. x1 minus 2x2 plus 3x3 is minus 2. Minus x1 plus x2 minus 2x3 plus 3. Let's look at that system. Again, to solve it, we're going to throw it in augmented form. And start doing our process. First variable I would keep the same. I'll add these two, 0, minus 1, 1, 1. This is row 2 plus row 1. And I could do here row 3 plus 2 row 2. This thing is that 0, 2, plus this 1 minus 4, that minus 1, 6 minus 1. So now I want to establish this as a pivot, kill that guy. Thank you. So multiply this by minus 1 to make that a plus 1 just to get into a nice form. And how can I make this a 0? I can just add those two, right? So I can take row 2 plus row 3. This plus this, 0. This plus that, 0. This plus that, 0. This plus that, 0. So now that's interesting. Now we're in an interesting situation. Because if I start at row 3, I get 0 equals 0, which is not wrong. It's just not helpful. Right? I can't conclude that this system has no solution. It didn't make a mistake yet. Okay? But there's a problem that arises here. You'll notice that what I have left over is that I have 2 equations and I still have 3 unknowns to solve for. There's no way I'm going to get to all the solutions, like specifically. But there might be a solution. So here's the process that we do. When this happens, and this being a row of zeros, or rows of zeros, do the following. 1. Identify the columns with pivots. That's the first step. I'm going to notice here, here's a pivot, so my first 2 columns have pivots. Okay? So I mark all my pivots. I mean, you don't technically have to do this, but you need to assess yourself where the pivots are. Take account of where the pivots are. That's the first step. Here's step 2. The columns that do not have pivots. The idea here is that anyone who does not have a pivot, the variable for that column I will set equal to some parameter. It will be a variable that can take on any value it chooses. The reason being, with these equations, the pivots mark the subject of the formula. So when I want to solve an equation, basically I'm going to move everything else to the other side. So I can do that for the x1 variable, I can do that for the x2 variable. The thing is I can't do that for the x3 variable. x3 seems to not be susceptible to a solving for it, so it can literally kind of be anything he wants. And so what I would do here is I would set x3 equal to, say, t, a parameter. And that t can be literally whatever it wants. I cannot force x3 to stick to an equation. Three.
Professor,
Yes.
so number 2 will say that the columns that do not have a pivot point allow their variable to be arbitrary.
Yes,
So
set their
even
variables equal to parameters.
R3, right? That
Huh?
does not have the pivot point.
There's no pivot in the x3 column,
X3 column.
so x3 is a parameter.
Okay.
Back substitute in the other equations. From the bottom up. As before. Okay, so now, row 3 didn't give me any information at all, but it does wipe out the possibility for me to be able to get x3 to be a subject of the formula for an equation. So what I do is I let x3 be anything. I can solve for x1 and x2, so that's what I'm going to do. So I'm going to go back and just like before, write down each equation and solve for it. So from row 2, I can see that x2 minus x3 is equal to minus 1. In other words, my x3 is what? It's t. In other words, if I say x2 minus t is equal to minus 1, so that means my x2 is t minus 1. In other words, when my x3 is allowed to be anything, my x2 is sort of allowed to be anything as well. It's just that it's off by one step in this case. So I set my x3 to be t, my x2 is therefore going to be consequently t minus 1, and then I go back into row 1. Row 1 says x1 minus 2x2 plus 3x3 is equal to minus 2. And now, basically what that means, I'm going to back substitute these guys into it. My x2 was t minus 1, my x3 was t. So this is going to be minus 4. Here I would get plus t, and I bring it to the other side, so it ends up being minus t. And what we want to note here these are solutions for any t value. So in other words, I can pick a value for t, and the vector comprised of those values will be a solution. Right? So if I pick, say, t equals 0, then the vector minus 4, comma, minus 1, comma, 0 will solve the system. I can pick t equals 1, and the vector minus 5, comma, minus 2, comma, 1 will solve the system. You realize that all these vectors, for any t value, it will be a solution to the system. So this actually leaves us in another case. As always, right solution is column vectors. There are reasons for this, but in the Mickey Mouse linear algebra class, we're not going to realize one. But it's nice. It's nice to have your solutions in terms of columns because it's easier to plug them into other things that we'll use later. So again, here x1, x2, x3. In this case, my x1 was minus 4 minus t. My x2 was t minus 1. And my x3 was t. And one thing we also like to do is separate. And this is something that we'll use in this class. When we get to eigenvalues and eigenvectors, you'll realize the importance of doing something like this. So I can put one vector here, and that's going to be where I throw in all my constants. all the numbers that are not multiplied by t, and every coefficient that is multiplied by t, I'm going to throw it on in this guy, the coefficients of t. So I split them up, things that have t and things that don't have t's. So what are the things that don't have t's? You have a -4 here.
-1.
-1,
0.
0. Things that have t's,
-1.
so we split it up, and that is how we would write the solution. In a larger context, the vectors that have the parameters attached to them, they're important in another sense. But for now, you just write the solutions in this way. This leads us to the third case. Infinite number of solutions. Notice that for every single t value, I will have a different solution. There's an infinite number of vectors that will solve this system. An infinite number of triples of x1, x2, and x3 will be a solution to this system of equations. Now here's an important theorem. It's not hard to prove, but this isn't a proof class. I'm not going to prove it for you, but it's a theorem. And the proof really relies on you just counting the number of pivots and comparing it to the number of columns, so it's not that bad. You'll realize that if, I can talk about here, the rank, that's the name of it, the rank of a matrix A is equal to the number of pivots in its reduced row echelon form. Right, so that's so for example, in this example, the rank was 2. In my first example, the rank was 1. Okay. So if we set B to be the augmented matrix, A with B beside it, and then I look at the rank of B, and now you kind of compare them, right? You end up with a bunch of cases here, and there are not that many. You can have the rank of A equals the rank of B. You can have the rank of A greater than the B. Rank of A less than rank of B. And rank of A equals n is the other case we have to consider. Assume this is an m by n matrix. This kind of gives you all the possibilities. Okay?
What's that above the B? You said B equals to A.
Where?
If set B equals A something.
If we set, I'm defining this other matrix.
It's just a vector.
Oh,
B is a vector.
okay.
What do you, this is what you're talking about?
Yeah.
Yeah, that just represents the column vector. That's the augmented form that we have. This is an n by n. So it turns out if the number of pivots is equal to the number of columns in the coefficient matrix, that sort of gives you a unique solution, because that means that every variable has a 1, and we can solve for it and make it the subject of a formula. If the rank of A equals to the rank of B, that kind of brings you to this case. So it's covered by this case. If the rank of A is greater than the rank of B, well, that's kind of impossible. If the rank of A, and that would mean no solution. If the rank of A is less than the rank of B, that's when you end up with, there's a column that doesn't have a pivot in it, and you can get to be, those guys get to be variables. So when it comes down to it, you just have really three possibilities. That's the theorem. That AX equals B be a system of linear equations. There are only three possibilities. For the number of solutions. One, AX equals B has no solution. This means it's inconsistent. Two, AX equals B has a unique solution. And three, AX equals, and by unique I mean exactly one. There's exactly one vector that solved it. Third possibility is A equals B has an infinite number of solutions. And there is no other possibility. These last two cases, it's called the consistent cases. The first case is called the inconsistent cases, but these cover all cases. You can never have a linear system of equations that have 5 vectors that solve it and no more. That's impossible. You'll either no vector will solve it, which it won't have a solution, exactly one vector will solve it, which means you have a unique solution, or an infinite number of vectors will solve it, which means you have an infinite number of solutions. Were you raising your hand?
Yeah, I was wondering why there can't be 2 or 3 or whatever solutions. I guess because it's only linear things we're dealing with, not
It's
quadratic.
because it's only linear.
Okay.
Right, so you can look at, for example, to illustrate, in the RT case, right? Basically solving a system comes down to you finding the intersection of 2 straight lines, right, in the RT case, right? Right, say something x plus something y equals a constant and something x plus something y equals a constant, and I want to find the solution to that system, you're just looking for intersections, right? So you have one case where you can have a line and another line, and they will only cross paths once, right? So this is the unique solution case. It is also possible for you to have a line, and a line that's exactly parallel to it, that is not passing through any of the same points. This is kind of the no solution case. But then what can happen is you can have a line, and you have the other line right on top of it. So the 2 lines coincide. Right? They might have different coefficients, but once you simplify everything, you will realize that all the coefficients are actually the same. And so the 2 lines coincide. And so one lies right on top of the other, and so every single point on either of the lines is a solution. Right? You can't have 2 lines touching each other in 2 places and no other place. It's not possible. Right? If something touches in 2 places and no other place, it has to be at least a quadratic. It won't happen with lines. And it won't happen with anything linear. It won't happen with planes, and it won't happen in any higher dimension when you're dealing with planes. Hyperplanes, it won't happen with either. Right? These are only the possibilities, and it comes down to you basically counting pivots and realizing either every column will have a pivot or every column won't have a pivot. If every column has a pivot, then that means that there is a unique solution. I can solve for x1, x2, x3, x4, all the way down to xn. If one of the columns in the coefficient matrix is missing, then I can't solve for that variable. It ends up being a parameter, and I get infinite solutions. The only other case is I end up in this situation where there's a row of zeros and the last line, on the last position there's a non-zero number, which gives me an impossible situation, right? So there's really only 3 situations. That's it for today. We'll do a lot more, but I want you guys to look at this case and just tell me the solutions here. We're not going to reduce. I'm going to give you a reduced form. Suppose a system in X, Y, Z, W reduces to. So I'm going to give you the matrix. This is after we did row operations to bring in reducer echelon. This is the, put the W in front. This is the W column, the X column, the Y column, the Z column. This is a constant. Tell me what the solution is.
There is no solution again.
Is that one the answer? I'd
There's
say
literally
two.
only one situation in which there's no solution, and that's not it.
You have 2
So-
variables.
That's
Right?
easy.
What's the only case that you would have no solution?
It's zero.
Oh,
Zero
That
is
number.
equal to
If
five.
you have a bunch of zeros and there's something over here that's non-zero, that doesn't happen. So there's definitely a solution here.
So
What would it look like?
It's in terms of 2 variables, right?
so W plus 3Y plus Z would be equal to 1.
What was the first step whenever you were in this?
Go from the bottom up.
Go from
Bottom
bottom.
up, yeah, but then
Let's say Z is
X
equal to
equals
T.
1 minus Y minus 2Z.
identify not everyone has a pivot. The first 2 columns have pivots, the last 2 don't. So that means,
Y equals the variable T.
yeah, set Y equals say T and set Z equals, I don't know. I don't like S, let's use R. And what would that tell you?
X equals.
Then you
1
move up to
minus
here,
2
you said
minus
X plus Y
Y
plus 2Z
2Z
equals
plus
1.
1.
So you have X equals 1 minus T
T.
minus 2R. You can also get, and that comes from row 2. Then you can look at row 1.
So W plus 3Y plus Z
Plus Z
equal.
equals 1.
So
So your W would be equal to 1 minus 3
T
T
minus R.
minus R.
What about if you
And so
limit, Professor?
Yes?
I mean, you are not defining, like, T and R does not have any value, right?
They can be any value. They're variables because they can literally take on any value. Any value you can think of and plug in there, any real number you plug in, will solve the system. And so in this case, my W is 1 minus 3T minus R. My X would be 1 minus T minus 2R. My Y would be T, and my Z would be R.
R.
And so what we can do here, again, we'll want to break this up in terms of the variables and the constants. Notice that there will be 3 sets of vectors that solve this. The ones that deal with the T's, the ones that deal with the R's, and the ones that have neither. So
So
it
1,
would
1, 0, 0, right? Negative 3, negative 1, 1, that's 0, and that would be negative 1, negative 2, 0, 1.
And that's how you'd write the solution in this case. Right, so it doesn't matter how many parameters you have to put. You can have several of them. There's not only just one. It's you literally look who has pivots, everyone who does not, all those guys get to be parameters. Alright? So we'll talk geometrically more about what this means next time, as well as we'll start to look at the determinant.
I've been seeing this almost every class.